Okay, so we are back on part M, and let's start the timer. The designer is creating an obstacle course where a person starts on a movable platform, height H, and they grab a rope, and swing down, and then they're going to let go, and they're going to fly across the debris of tar pits, and say the designer makes some observations. Why does a person land in the moat if the rope's length is very short? If the rope is short, then the gravitational potential energy of the person is small. Right. So if the rope is short, then they don't get enough energy transformations from potential energy into kinetic energy to give them enough speed to go across the moat. They have to have enough x velocity to get across the moat and the amount of time that they're going to be in free fall as they fly across the moat. All right. Why does a person land in the moat if the length is too small? That's because you're not going to have enough time to get across the moat. Now you're going to have a lot of speed, but the amount of time you're going to be in free fall from when you let go to when you hit the ground is going to be tiny, right? You're not going to have enough time to fall. The time that you're falling will be so small that you're going to land in the moat. That's gross. If you knew what was in a moat, that would just make you throw up in your mouth. All right, so using the variables given, write mathematical expressions for the horizontal speed of the person at the moment they let go. So the gravitational potential energy they have is equal to the kinetic energy they have. The mass cancels. You multiply both sides by 2, and you take the square root. And the distance that it falls is equal to the velocity times the time. So we already have the velocity, root 2gl. The fall time is our old friend from kinematics, t equals 2y over g. The displacement is h minus l, the height minus the length of the rope is how far we are falling. And so that's from our old kinematics equation. And so you multiply them together to get the distance. And when you multiply roots together, apparently we can take the square root of 2 times the square root of 2 out and make it 2. And looks like the g is going to cancel the g. And we're going to have L times quantity h minus L, or HL minus L squared. If L approaches 0, D also approaches 0, because the square root of 0 is 0. If L approaches H, then H minus L is 0. Square root of 0 is 0. There we go. Nice. N. We did N already. Because it's springs, I recognize this. I can skip this. I think we did O also. No, we didn't. I'm just joking. We definitely did this last week. I remember this. Definitely. All right, so we're on the last one. We have 6 minutes. Cool. So here's a roller coaster on Jupiter. And it's a fake Jupiter. It represents Jupiter, and then the next one represents Neptune, and then back to the ground, scale of the planets. All right. Two engineers are extremely concerned about the safety of this coaster. If the normal force becomes any number less than 0, the cart loses contact with the track and becomes a projectile. All right, so the system consists of a cart and the Earth. So at the top of the first Jupiter hill, the energy of the system is all gravitational. At the top of the second Neptune hill, the cart system will still have gravitational potential energy, and this time the cart will also have kinetic energy. The energy at the top of Jupiter and the energy at the top of Neptune are equal, right? The gravitational energy is mgh. Solving for the speed at the top of the hill. And wow. So you should enjoy processing that. My head hurts. The normal force of the cart when it's on top of the Neptune sphere So the net force, which is the force of gravity minus the normal force, is equal to the centripetal force. Centripetal force is mv squared over r. Force of gravity is mg. We can't cancel the m's because normal force is what we're looking for. So we swap things around so the normal force is by itself. And then we distribute the m out. And then 4g r minus r over r is what they're using for v squared. Yeah, I'm not going to lie, I'm not really sure where that came from. Oh, there it is, right there. We used energy to figure out what v was equal to in terms of r, big R and little r, the radiuses of the two planets. All right, so we have there it is. So they have the potential energy on Jupiter is equal to the kinetic energy on Neptune plus the kinetic energy or potential energy on Neptune. And if you solve that for v, which is by itself, and do a bunch of algebra, you will get the expression 2 root g difference between the radiuses of the two planets. So then they squared that, and they put it in here. And when you square whatever that was, you get 4g, the difference between the two radiuses. Right. And then they distributed and multiplied 4g by r and 4g by little r. And now everything's got a g in it, right? They divided everything by little r, I mean. So that you had g minus plus 4g, that makes a 5g. And then the g's canceled, and basically the difference 4 times the radius of Jupiter divided by the radius of Neptune subtracted from 5 times mg will give you the normal force. So the last step supports B's claim that the differences of the planet's diameters are too large, the speed will be large. Step 4 supports C's claim that if r is too small, then v squared r becomes large, which makes g minus v squared r very small or possibly negative, and the cart would fly off the track. Whew, is this ride safe? If Neptune is not safe, which planets could be safe? If the normal force is less than 0, that's not safe. The minimum possible radius for the second hill can be found by making the normal force greater than or equal to 0. So therefore, the diameter has to be greater than or equal to 4/5. The diameter of a little planet has to be at least 80% of the big planet. So Saturn would work. Neptune won't work. Whew. And thus ends the lesson.